Okay, welcome everyone to tutorial workshop 8. If you can hear me, just raise out your hand. Okay, thank you. So we will be going through the summary and at the same time we will be looking at the exercises also in the tutorial worksheet. So what you have to do now is you have to open the two files, the summary notes and also the worksheet together. So when we talk about the certain application, then we will jump over to do the calculation. Okay. So are you ready with the two files open? Summary notes and the worksheets. Okay. So let's go through the summary. Electromagnetic induction and Faraday's law. Right? So the first sentence in your summary notes, this one, this is our one and only one concept in this topic. So if you say this topic is very difficult, it is not too complicated that it has a lot of concept. Okay? It's easy because it has only one concept. So look at the keywords here. Changing magnetic flux induces current. Okay, so it's not magnetic flux induces current. It's not maximum magnetic flux induces current, but the word here is the change. Okay, the triangle. So it must be a changing magnetic flux induces current. Okay. So it is easy because it's only having one concept. It's somehow difficult because most of the students, they cannot get what it means by changing magnetic flux. Okay, so as long as in your mind you have that it must be a change in magnetic flux, basically you have mastered the topic well. Right, so what is actually magnetic flux? Look at the definition. It's the total number of magnetic field passing through the area that enclosed by a loop. So let's say if in the on your screen here, yeah, this is a region with magnetic field which is going into the page. Right. If I do not put anything here, there is nothing here. Do you have magnetic flux? No, yeah? Okay. If nothing is being placed here, so no magnetic flux. Okay, so what if I place my coil inside here? When you place a coil here, then there is magnetic flux. So this magnetic flux is equivalent to the magnetic field times the area of the coil cos theta. Okay, whereby the theta refers to the angle between the normal line to the coil and the magnetic field lines. Okay, so in conclusion, we can say that magnetic flux here So in conclusion, we can say magnetic flux is actually the amount of magnetic field that passing through a coil here. Okay, it refers to the total number of the magnetic field lines that pass through a coil. Okay, so how do we determine the normal line? So usually, let's say if now we are looking at different angle. Okay, now this is the magnetic field. So if your coil is placing like this, if this is your coil as area, yeah. So in order to find the angle, the first thing that you have to do is to draw the normal line. So from the normal line to the magnetic field, that is your theta, right? So whenever there is a change in this magnetic flux, it can be either a change in your magnetic field, or the change in the size of your coil, or even the orientation of the coil. Okay, so as long as there is a change in either these three, then there will be a change in magnetic flux. So when there is a change in magnetic flux, you get your induced current, right? So the second terms, which is the main dish of this topic, the Faraday's law. So Faraday's mention about the induced EMF in a coil is directly proportional to what? To rate of change of magnetic flux. So if you write them down in the equation, okay, is actually depending on the change in flux over change in time. Okay, whereby n here is the number of turn of the coil. This is magnetic flux, and this is time in seconds. Okay, so magnetic flux given by BA cos theta. B is the magnetic field in the unit of Tesla. A is area of the coil in the unit of meter square. Theta is the angle between normal line and the magnetic field. Okay, so if you look at here, the negative in the equation direction, which is further explained by length. So it does not reflect the magnitude. It tells you about the direction of your induced EMF. So it says that the current produced by an induced EMF move in a direction so that its magnetic field opposes the original change in flux, which means the induced current so every current will produce magnetic field, right? So let's say the magnetic field produce lagging. How about now? How about now? Is it okay? Better, huh? Okay. I moved nearer to my Wi-Fi. Okay, so induced current will produce induced magnetic field, yeah? Okay, every current will produce magnetic field. Same goes with the induced current. So let's say the magnetic field produced by the induced current is induced magnetic field. Okay, so according to Lenz, this induced magnetic field must oppose the original change in okay, so this are the relationship. Okay, so according to our main concept, one and only one concept, the changing magnetic flux induce the current. So the current will have to move in a direction whereby its induced magnetic field will oppose the initial change in flux. So there are two types of magnetic field. One is the original magnetic field, which is changing. The second magnetic field is the magnetic field generated by the induced current. Okay, so how are they actually related? They have to oppose each other. Okay, so in order to help you to determine the direction, these three steps has to be followed. All right, so the first step, determine the change in the flux first. So this is the original magnetic field. How does the original magnetic field has changed? Okay, so from the change that you have identified, then you have to oppose. Okay, oppose the change. So the keyword there is Lenz. Okay, Lenz tells you that it must oppose. And finally, determine the direction. Okay, so to find the direction, use right hand grip rule to determine the direction. Okay, so look at our first application, a moving conductor. So for moving conductor, your induced current can be found from this equation, VLV cos theta. B is the magnetic field. L is the length of the conductor. V is the velocity of the conductor. Okay, so let's use the steps in order to determine the direction of magnetic field. All right, so look at the diagram. This is the initial area before, yeah? The initial area. So when the conductor the sound is not clear. Choppy, huh? How about now? Is it better? Okay, so let's continue. Alright, so let's determine the direction by using the 3 steps that introduced. So when the conductor is initially here, okay, this is the original position. So your area covered by the whole coil or the whole loop is here, right? The one that's shaded with orange color. So after that, you see the velocity, okay? The direction is being dragged to right hand side. So let's say this is your final position. Okay, so if you compare now the magnetic flux, so the final area now covered by the whole loop is shaded by green color, isn't it? So if you compare the magnetic flux before and after, is there a change in magnetic flux? Yes, right, there is an increase in the magnetic flux. Okay, so what is the direction of the original magnetic field? It is an increase of the cross product, increase of the magnetic field which is going into the page. Okay, so if you look at the diagram here, also very clear. So if you look at here, initially your initial magnetic flux, how many cross product inside? 1, 2, 3, 4, 5. Okay, initially you have 15 cross product inside, right? So once the area has been increased, so you go and count how many cross product inside. It becomes 18 cross product, isn't it? So in your first step, to monitor or to identify the change in the flux here, there is an increase of the cross product. So once you have done your first step, it is easy to write the following steps. The second step is to oppose the change. So in order to oppose the change, you have to decrease. If your observation, okay, it's an increase, then to oppose you have to decrease. So copy the same thing, decrease the cross product. So if you would like to decrease cross product, what should you produce? You have to produce dot product, because the dot can cancel off with the cross. So now using right hand grip rule, so this is right hand grip rule. In order to produce dot product means coming out from the page. Now with your right hand, the thumb is coming out from your computer screen. Where is the directions of your current? It is moving anti-clockwise. So anti-clockwise, this will be the direction of your induced current. Okay, So I want you to look at your worksheet. Drag down to 8.3. Can you do the same steps in order to look for the direction? Okay, so if you would like to find the magnitude using the formula, since this is a moving conductor, VLV cos theta. Okay, so your theta here is equals to 0. So cos theta equals to 1. B 0.75. Length given by 30 centimeter, convert to SI unit 0.3. Velocity 1.9. So you get 0.43 volts. So your task now is to look for the direction. Write down the 3 steps. Change in flux according to length. And finally determine the direction. So I give you 2 minutes to do so. You write your answer on the chat. What is the direction of the induced current? Okay, very good. Clockwise. Right? So how do you get that? Firstly, observe the change. So the conductor is being dragged upwards, means magnetic flux increases. So what is the direction of the magnetic field? It is a dot product. So according to length, I have to oppose the change. So since the change is an increase, so to oppose, I will have to decrease the cross product. So to decrease the cross product, I will need to produce a cross product. So from the right hand grid rule, to produce cross product going into the page, your finger shows that the current has to move clockwise. So very good. Okay. Next, look at the second application, the generator. So generator equation in order to find the value of generator is given by N B A omega sine omega t. N equals to number of turn, B is the magnetic field. A is the area of the coil, okay, which is here, area of the coil. Sine omega t is equals to the angle in radians. Okay, so look at your worksheet section 8.4. The sample of calculation. So a simple generator has 320 loop. That is your N. A square coil. So this is the length or the width. Okay, you can say the length of the width because your coil is now a square. How fast must it turn in 0.62 Tesla in order to produce? So your V0 is 120 volt, which is the peak output. Peak means this is maximum value, yeah? So from your generator, MBA omega sine omega t, if it is maximum 120, which means your sine omega t is equals to 1. Okay, N is 320, B is 0.62. Area, since this is a square, so 0.21 times 0.21. Omega is your unknown. So solving this, you get 13.7 radians per second. So what can be done if you would like to increase the output voltage? So you can increase number of turn, you can increase magnetic field, you can also increase area of the coil, increase your angular velocity. Any factor in here can be increased in order for you to increase your maximum voltage. Alright. So back to the notes. Looking at the third application, the inductor. So for inductor, the factor of change that causes in the change in the flux is due to the change in current. So when there is a change in current, resulted in a change in magnetic field. So finally, it results in the change in magnetic flux. So look at the first one. When the power supply is just connected to the inductor. So in this case, the first diagram, no current, so magnetic flux also equals to 0. At second diagram, when the current is connected, so let's say current move in this way. This is the current from the power supply. So when current passing through your inductor like this, isn't it? There will be magnetic field passing through your coil. According to right hand grip rule, you will get a magnetic field which is moving downwards, and it is at the maximum now. Okay, so if you compare to before and after, is there a change in magnetic flux? Yes, right. So the change is definitely an increase of magnetic flux. So the direction of magnetic field is moving downwards. According to Lenz, in order to oppose, then I would like to decrease the magnetic field which is moving downwards. So have to produce magnetic field which is moving upwards. So based on your right hand grid rule, if I would like to produce magnetic field which is moving upwards, then it will be moving anti-clockwise from the top view. Okay, so if I would have to draw the induced current in my diagram, so anti-clockwise, it will be like this. Anti-clockwise coming out from my inductor. So this blue color will be my induced current. Okay, so this current is actually coming out from inductor. Why is first one going up? Which first one going up? You mean the blue color or the red color? Up. The blue color, you mean the blue color, why is it delta something P? That means increase. This one means increase. The change in the flux from before and after is an increase of the magnetic field which is going downwards. This one means decrease. According to Lenz, you will have to oppose the change in flux. So if you monitor the change is an increase, so when you would like to oppose, you have to decrease. This is not going up or this is not going down. On the front part here, it means here, this one means it is increased, means your magnetic flux increasing. So that is your observation from before and after. Alright? When it comes to Lenz, look at the definition, all right? It has to actually oppose the initial change in flux. So once you have identified your change is an increase, so in order to oppose, what should you do? You just decrease it. So it does not related with your directions of magnetic field. It's only show increase or decrease. You can write down increase or decrease, okay? However, if you are very fast, you want to do it fast, you don't have to waste your time to keep on writing down increase or decrease, okay? Yeah, please listen, huh? My stylus don't want to cooperate with me, and my laptop also dying soon. Okay, so look at the next one. Now listen properly. So from here, when you have power supply, the current, again, look at here, yeah? So initially, when you have current which is equals to the current from the power supply, the one represented with red color. So when current passing through your solenoid, what is your magnetic flux? Isn't it also equals to the maximum? Like this one, yeah? Right. So based on your right hand grip rule, the direction of magnetic field passing through your coil is actually going downwards, right? Okay. So the next moment, this is before, this is after. So the next moment, you turn off the power supply. Okay. So when you turn off the power supply, what happens is no more current from the power supply. So current equals to 0. What happens to your magnetic flux? When there is no current, magnetic flux also equals to 0. Okay, so now, can you tell me what is the change in flux? It is an increase or decrease? Decreasing, yes. Okay, so decreasing. Very good, huh? Okay, decrease. So I use symbol going down, or if it confuses you, okay, it actually means decrease. Okay, the change is a decrease in the magnetic field which is going downwards. So in order to oppose the change, what should we do? Since the change is a decrease, so I increase. Okay, so increase this magnetic field which is moving downwards. So if I would like to increase the magnetic field which is moving downwards, I should produce magnetic field which is moving downwards. Okay, so finally, using your right hand grip rule to determine the directions of induced current. Okay, using your right hand grip rule, thumb going downwards. So now look at your finger. It is actually clockwise from the top view. Okay, so now label the induced current in your diagram, yeah? Clockwise on the top view, isn't it? Like this. So that will be your induced current. Okay, it's actually the same direction as the current from the power supply. Okay, so the application of Lenz's law, in order to determine the direction of induced current, this is a compulsory question in your final. Alright, so you might think that why am I using so much time to keep on going through the example with you? Because that is definitely the compulsory question that will be coming out in your final. So it seems to be very not really difficult, but the most difficult part is as long as if you can determine your step 1 clearly, okay, the observation of the change, if you can write them down correctly, for sure whatever that you write behind will be correct. All right, so now let's look at your worksheet 8.5 about inductor. So the solenoid is connected to the power supplier with N turns, with area, the length of solenoid, and the current is I. So derive an equation for self-inductance L of the solenoid. So self-inductance is the one that the unit in Henry, if you remember, yeah. Okay, so for inductor, the induced EMF, okay, induced EMF is equals to negative L times delta I over delta T. Okay, and every electromagnetic induction, they all follow Faraday's law, which is this one. Negative N times the rate of change in magnetic flux. Okay, so you have to further expand your change in magnetic flux. Magnetic flux is BA cos theta. So simplify the equation by moving out the constant. So in this case, the factor of change is because of the current. So current will affect your magnetic field. So you will get delta B over delta T. So this magnetic field is because of your solenoid, right? So you have to write down the, okay, expand this one is equals to the magnetic field of solenoid, mu Ni over L. So plug in by moving out all the constant, mu naught N over L, so you get delta I over delta T. Okay, so this one, copy them down. Copy down. So delta I over delta T can be cancelled off on the both sides. So finally, simplify your equation. You get mu naught N square A over L. Cos theta here is equals to 1. Okay, why? Because according to your right hand grip rule, isn't it? Let's say if this is the directions of your current from the power supply. So when your current passing through your coil, you get a magnetic field which is moving downwards, right? And the 90 degree or the more normal line to your plane of coil, this is your plane of coil, right? So the normal, this is the normal line of your plane of coil. Isn't it your theta equals to 0? So when your theta equals to 0, your cos theta equals to 1. So this is the derivation, okay, in order to get the formula for your self-inductance. So if N equals to 100 turns, A is 0.3, L is 5 centimeter. Calculate the self-inductance of the solenoid. So mu naught is the constant, 4 pi times 10 to the power of negative 7. Number of turns given 100. Area 0.3 centimeter square, convert to SI unit times 10 to the power of negative 4, divide by length, which is 0.05. You want to see the equation here. Okay. So from the calculation, you get 7.54 times 10 to the power of negative 6 henries. Yes, according to your syllabus, but since you are having open book tests, if you didn't remember also, I don't know. Okay. So, usually it will be more to application, whereby you need to do the calculation or you have to do explanation. The direct question like this will not be set in the final. Okay. Wow, explanation. Not bad, your explanation. Okay. So don't have to worry. So what is the total energy that can be stored in the inductor? Total energy in inductor is given by half Li square. Okay, so predict the direction of the induced EMF from the inductor when the switch is just closed. Induced EMF from the inductor. So the one that we have looked at just now, the directions of magnetic field is going downwards, right? So write down the 3 steps. Predict, observe the change, oppose the change, and finding the direction. So observe the change. When the current flows through, there will be an increase of the magnetic field which is going downwards. So in order to oppose the change, you have to decrease the magnetic field which is going downwards by producing magnetic field which is going upwards. So to produce the magnetic field which is going upwards, according to right hand grip rule, here use blue color, you will get a directions of going like this, right? This is the directions of induced current. So when it passes through your ammeter, is from left to right. Okay. Done? So now look at mutual inductor. Mutual inductor happen when there are two solenoid or two inductor sitting side by side together. So the application is the transformer. When it is a step-out transformer, it means the number of turn at your secondary coil is larger than the number of turn of your primary coil. Okay, so the when it is a step-down transformer, means secondary coil is now lesser than the primary coil. Okay, so both of them share the same equation. Okay, the ratio between the secondary to the primary is equals to the voltage. Oops. Okay, voltage of secondary over the voltage in primary coil. However, current is the opposite way. Is primary over secondary. So both of them using the same ratio in order to find the voltage current or the number of turn. So let's go back to our 8.6 and do our calculation. So transformer has a primary coil. This is your NP of 100 turns, secondary coil of 200,000 turns. An alternative supply. So this is primary coil, so this is B primary. Current in primary is 100 ampere. So is this a step up or step down transformer? Okay, so since secondary coil is larger than your primary coil, so it is a step up transformer. Calculate the output voltage. Okay, so write down the ratio. $200 over 100 equals to Vs is what you have to calculate. So you get 480,000 volts. What is the current in secondary coil? So current is the other way around, huh? Primary is given by 100, secondary is unknown. So 0.05 ampere. Can the alternating power supply be replaced with direct supply? Yes or no? No. Why? Yes. Okay. Can you give me answer? If you give no, why? Yes, why? It's an open discussion. Yes, why? No, why? No change. No change in magnetic field. Okay, very good. Okay. So, to be strict, yeah, if you say you want to replace with direct current, you can actually, but yeah, in order to provide a constant change in magnetic flux, what you should do, you have to hire someone to stand in front of the switch, keep on turning on off the switch, keep on off the switch for 24 hours 7 days non-stop. Then the transformer can only be worked under direct current, because when you turn on and off the switch, you get to result a change in the magnetic flux through the primary coil, right? Okay, so technically yes, you can do it, but you have to put in extra effort. So that's why physically, you know, I mean, like whether is it feasible or not, or is it economic or not, it is actually not. Yeah, so for this one, we won't be replacing the alternative power supply to the direct current. Why? Because you get the right point, huh? Direct current cannot supply constant or direct current only. Direct current constant value of okay, because direct current will only provide constant value of current, so which will not result in any change in magnetic flux, unless you go and hire someone to stand in front of the switch and keep turning on off the switch. Okay, then it is feasible. However, it's not, we would say it's not economic to do so. Huh? So if this last time when the question was first came out in the final, those who answer yes, right? I say next time when you become engineer letter, I would want to see you to build a transformer which can be supplied by direct current. So please hire someone to stand in front of the switch to turn only on off the switch. Okay, so let's take a break of 10 minutes before we look at the first two sections, the first two main dish, I mean like the most important part in this topic. So we will come back at 2:10 later, right? So if you have any question about just now, you can stand back and ask. Okay. You mean DC? DC is direct current, no? AC is alternating current. Time and current. So for DC, it's just like when your heart, I mean like when someone's heart stop beating, right? You get a straight line. So if you look at the current supply here, right? It's actually the same. So when your current supply is constant, your magnetic field is also constant, right? So when your magnetic field is constant, there is no change in magnetic flux. Unlike the AC current, if it is AC, you get changing current all the time. If you look at the graph, your current, the value of current changes all the time. So your current is not constant. So when your current is not constant, the magnetic field also not constant. So magnetic field not constant means there is a change in magnetic flux. So that's why alternating current is feasible to be used in order to be applied into the transformer, because transformer is being operated due to the magnetic induction, whereby it needs the change in magnetic flux. Okay. What is your question, huh? Change in magnetic field causes induction, like storing a magnet on a nail. That one is because of I guess you are confusing the one. That one is electromagnetism only, huh? Okay, so you look at here. The one that you mentioned is electromagnetism, like you are coiling your wire. Okay, you put around a nail, is it? Then you coil your wire around the nail. Is this what you mean? Then you connect. That one is only magnetism. That is last week topic, magnetism. So when you coil your wire around the nail and you connect them to a power supply, so the whole things here will be turned into a magnet. Then when we have current flowing through the coil, so the whole things will be turned into magnet, whereby here becomes your north pole and here becomes your south pole. So that was your topic 7 last week. How do we get magnetic field from current? So for this week, topic 8, what we want to see is how do we get magnetic field from, how do we get current from magnetic field? So it is actually means the changing magnetic field or the change in magnetic flux will induce current. Is something that is already advanced, okay, as compared to this one only, huh? Okay, so for this one, what you have to take note is the change. You have to look at the change. Okay, take note on the change in the magnetic flux. Okay, so for this one, that's why the first part you have to know what is magnetic flux, and second one you have to observe the change. 8.4. Okay. Okay, so welcome back and let's look at 8.1. How to find magnetic flux. So for this question, I would like you to open on your Moodle, go to topic 8. So when you click into topic 8, you will see a series of things here, right? So I would like you to click on this game, Crypt Text. So it is actually a game like word search. You can get your answer in here. Okay, so how do you find the answer inside? So based on the question, look at the question here, and the answer has been given to you in 0.0 something, right? Okay, so if you look at the answer there, it's 0. So I write down somewhere here. Answer there is 0.0 something Weber. So if your answer, let's say when you calculated, you get 0.0 like say 20 Weber. So this 20, instead of writing in numerical number, okay, you have to turn it into alphabets. So 20 is 20. So you find the word 20 in the word search. Okay, you find the word 20 in the word search. Then you click answer and you write down. Right? So if let's say it is 22. So what you have to write down there is 22 without any space or any dash. Okay? So I give you here 1, 2, 3, 4, 5 questions. I give you 5 minutes. Is it too short? Okay, 7 minutes for you to complete this part. Then we will discuss the answer together. Yes, has to be in big letter, big capital letter. Wow, Hedges is the first one to complete. Oh, is it? Not yet. You must get 100. Not yet, not yet. Okay, I haven't seen anyone got 100 yet. No? Faster, faster. How does it work? You mean how to find the magnetic flux? The value that you have found, the two number behind it. Cannot type in your answer. You click answer, then you type here. Wait. Here, the next to the questions, you click the answer button, so it comes out a window, right? So let's say if your answer is how much? $46. Okay, 0.046. So you type 46. Okay. It can work, huh? If you key in the answer and when there is no response, means the answer is incorrect. Huh? Yeah, congrats to Hedges. Huh? He scored all correct already. Any more? Yeah, we have our second one, Sherry Tang. Yeah? Okay, so I think we will proceed with our answer discussion. So the questions are actually from your 8.1, so it will choose randomly from there. You can try again until you get all correct. Huh? Okay, but now we will go through our answer together. Okay, so one turn circular coil with radius of 14 centimeter oriented where the plane of coil is perpendicular with the directions of magnetic field. Okay, so let's draw the diagram first. The coil is being oriented where it is perpendicular. So this is how your coil is oriented, perpendicular to the magnetic field lines. Find the magnetic flux for the following. Yeah? So this is the initial orientation. The coil is rotated 30 degrees from the original position. This is the original position, 30 degrees. So becoming like this. .30 degrees from the original position. So In order to find your magnetic flux, you have to first determine your normal line, the normal line. So the angle between normal line and your magnetic field is theta. So in this case, your theta is equals to 30 degrees also. So magnetic flux BA cos theta, B 0.75, area is pi r squared. R given by 14 centimeters, so it's 0.14 meter. Cos theta, which is 30. So 0.040 Weber. So if you get this question, your answer is 40. Yeah? Question B, the coil is rotated 360 degrees from the original position. So 360 degrees means back to the original position. Okay, so first find the normal line here. So theta is 0 degree. Magnetic flux 0.75 A pi r squared cos 0, which is 1, so you get 0.046 Weber. The coil is rotated where the angle between the plane of the coil is 60 degrees relative to the magnetic field. So this is your magnetic field. The coil and your magnetic field is 60 degrees. Okay, firstly, draw your normal line. Angle between normal line and your magnetic field lines. So it is 90 minus 60, 30 degrees again. Cos 30, so you get 0.040 Weber. Question D, the number of coil is increased to 10 turn. There won't be any change. Yeah, your new magnetic flux is still equals to your original magnetic flux, which is 0.046 Weber. Right, if you look at your magnetic flux equation, only equals to BA cos theta. So even though your N has become 1000 turn, your magnetic flux still remains the same. Okay. E, the coil is stretched to double the original size, means now your A prime is equals to 2A. So your new magnetic flux is equals to B times your 2A. So you get 2BA cos theta. So it's actually 2 times the original magnetic flux. Okay, 0.092 Weber. The coil is dragged to a region without magnetic field. So this one, magnetic field is equals to 0. So the new magnetic flux is also equals to 0. Question G, the coil is dragged until 50% of the area of the coil is covered by magnetic fields only. So which means now the area that covered by the magnetic field, in this case, is half of the original area, because only half of the area is being covered by the magnetic field. Okay, so new magnetic flux so it is half of the original magnetic flux. So 0.5 times 0.046, you get 0.023 Weber. Question H. The magnetic field strength is reduced by half. B prime is equals to half of B. So new magnetic flux is equals to half again. So 0.023 Weber. Okay, so this is how we determine the magnetic flux. So once we have known how to look for magnetic flux, now let's apply them in Faraday's law calculation and use Lenz's rule to look for the direction. So also this one I will give you some time to try. Okay, to try first. But I will go through the first question with you, yeah? Then 2, 3, 4, 5. There are 4 questions that I would like you to try your own and you give me the answer. Okay, so this is question question 1, 2, 3, 4, and 5. So I will start at the middle, yeah? Okay? So question 2, what you have to do is you tell me what is the direction of induced current. Okay, so question 2, Azim. You have to tell me the direction. Question 3, Ilan. Okay, use the 3 steps that you have done before to determine the direction of the induced current. Question 4, Han. Yes, huh? You tell me what is the direction of induced current in question 4. And June 3, you are question 5. You can type on the chat, you can type on the chat, or you can actually open your mic and call out the answer, right? So I will go through the first question with you all, then I will give you 5 minutes. The rest you have to try also in both the calculation and also the direction. Now let's look at the first question. So the coil is shrunken to half of its original size in 0.2 seconds, while the magnetic field is kept constant at 0.75. Okay, so if you look at here, now let's say, okay, the original area is given by, the radius is 14 centimeters, so area is pi times r squared. So you get 0.0616 meter square for the original area. Magnetic field 0.75, and theta is 0 degree. So after, now your A prime is reduced to half of the original size, right? So means half of your A. So it's 0.0666 is 3, 0.0308 meter square. Magnetic field remain constant, the same 0.75. Theta doesn't change, equals to 0. So in order to find your induced EMF from Faraday's equation, expand BA cos theta over delta T. Cos theta equals to 1. Number of turn also equals to 1. Okay, so simplify by moving out the constant. B is the constant. No, number of turn is not equals to 1, is 10. So move so left only change in area over change in time. So plug in the value. This is A prime minus your A, huh? B 0.75. A prime is 0.0. Divide by time, which is in 0.2 seconds. So you get 1.155 volts. Okay, finding the direction. The 3 steps. So if you look at the diagram, the change in the magnetic flux is, and a decrease, right? A decrease in the magnetic field which is going into the page. So according to length, I would like to increase the cross product. So have to produce more cross product. So in order to produce the cross product from my right hand grip rule, the directions of current is moving to the left when passing through your ammeter. Okay, this is your ammeter. It is actually moving clockwise. Okay, so for the remaining 4 questions, I give you again 1 question 2 minutes, so 8 minutes to complete them. And I shall wait for your answer, yeah, Azim, Ilan, Han, and Jung Fui. Okay, you just tell me the final directions of your induced current. You can't see your question? It's on your tutorial worksheet. Download it on your Moodle. You are question number 4. Example solution from the first one here. 4.51 anti-clockwise? Your question. Okay. Your question is this, huh? So let's say if this is the top view. So anti-clockwise is from which view? From here or from here? Or can you tell, is it from the top view if this is where your emitter is placed on? So on the top view here, how does it go? Okay, your 0.77. Very good, correct. Clockwise. View from top is clockwise, but how leh? This one, like, is it going like this or like this? So wait, element number 3, clockwise. It's not clockwise, it's anti-clockwise. Okay, the first question you mean has to produce dot product? Why need to produce dot product? Because we want to increase the cross product. So if we want to increase cross product, we have to produce cross. If we would like to decrease cross, then only we produce dot. Okay. Okay, Azim, what is your answer? So Ilan have already found this one to be 0. The value is 0.77 volt, correct? But the direction is not clockwise, no? Done. So far, Azim and Junhui haven't replied anything yet. Are you there? Hello? It's like when I hello, there is some echoing because no one answering back. Oh, you all fall asleep already, huh? Oh, am I disconnected? How about the rest? Okay, so let's look at number 3 first. So Elan has already helped us to find the value of induced EMF. Okay, so let's see how can we get the induced EMF. Look at number 3. To 1 Tesla in so your area, let's write down their property. The area is the same, 0.0616 meter square. Magnetic field here is 0.7. So after, your A prime is the same, doesn't change. What change is your B prime has changed to 1 Tesla. Theta still equals to 0. Okay, so start from your Faraday's equation. Expand the equation. So put the constant inside the after the delta sign. So move all the move all the constant before in front. So since B is the factor of change, cos theta is equals to 1. So move your A in front, left delta B over delta A. So put in the value. 10, area 0.0616. Delta B is B prime 1 minus 0.75 over the time. So we get negative 0.77 volts. So if you want to remove the negative also can, okay? Because negative only shows the direction. Now, how do we determine the direction? Okay, so firstly, observe the change. From before and after, sorry, this should be before, this should be after. Okay, when your increase, yes, very good. So when the magnetic field increase from 0.75 to 1 Tesla, it means the change is an increase of the page, so increase in cross product. According to Lenz, since the observation is an increase, so I would like to oppose. When I would like to oppose, I will decrease the cross product. Very good. So to decrease cross product, I have to produce dot or cross, dot or cross, dot or cross. dot or cross. I have to produce dot. Very good. Produce dot. Because I have to decrease cross, right? If I have to decrease cross, I have to produce dot, because the dot will cancel off the cross. Okay, just like how you play games. Yeah? If you have too many army, then you have to produce more enemy to kill your army. Can it be work like that? Yeah, something like that. Okay, so now once you have determined, your answer later. So once you have determined the directions of the magnetic field that you would like to produce, which is dot product, now use your right hand grip rule to check on the direction. So the dot product coming out from the page, so your finger shows that it is actually clockwise. So when passing through your ammeter is from left to right. Okay. Magnetic field keep constant to be 0.75. Theta, initially it is 0 degree. Alright. So after area remain the same, magnetic field 0.75. The plane is rotated 60 degrees from its original position. So this is the original position, right? Or we just draw somewhere here. 60 minus 0, correct? Yeah. So this is the original position. It's being rotated from 60 degrees. So your theta, angle between normal line and your magnetic field line, is 60. So theta is 60. Very good. Now let's do our calculation to find what is the induced current. Expand the equation. The changing factor is your theta now, is it? So move all the constant to the front and left cos. Ooh. Okay, change in cos theta over change in time. Negative 10, 0.75, area 0.0616. So this is cos 60 minus cos 0 divided by 0.2. So you get 1.155 volts. Okay, so take note, if there is a change in the angle, the common mistakes that to this. Zero, so it's actually equals to cos 60. In fact, it is not, because if you look at the delta here, it is actually delta the whole thing. It's delta the whole thing, so you have to cos 60 minus cos 0. Alright, so this is wrong. Okay, now let's check. So this is top view. From before and after, what is increases or decrease? It is actually, yes? Increase. Decrease, right? You see the here, this is your coil. So if you look at here, how many line has passed through your coil? 1, 2, 3. Correct? But look at the diagram after. How many magnetic field pass through your coil? Only 1 and 2. So it's actually a decrease in the magnetic field line, which is moving to the right. So according to Lenz, since the change is a decrease, so you would like to increase magnetic field lines, which is going to the right. So if you would like to increase magnetic field lines, which is going to the right, so you have to produce magnetic field line, which is going to the right. So based on your right hand grid rule, in order to produce magnetic field line which is going to the right, now your thumb shows to the right. Okay, clockwise from which direction? Yeah. So now if it is from the top view, so move your head above your finger now. So your finger, isn't it pointing downwards when it is below you? So the directions of current from the top view is going downwards like this, right? So if clockwise, it depends on which side you are viewing. Okay, so now on the top view, right? Get it? Okay, so let's 5. Okay, so Junfui has already mentioned the correct answer. Okay, direction is clockwise. So it is clockwise, yeah? So we shall go through together how to get this. Yes? Anything? Yes, anything? Or would you like to type your question? Oh, Question 4. Okay, it's okay. Question 4, this is from the top view. Top view. So, if it is from the side view, if this is from the side view, then you might get something like this. This is your coil. The directions of the magnetic field is going into the page. Right. So if it is from the top view, this is what we can see here. The top view. Okay. So let's see from the top view, from the perspective of the top view. Yeah? So if step observing the change from before and after, yeah, the change in magnetic flux, the magnetic flux at after is lesser as compared to the magnetic. So the change here is a decrease in the magnetic field which is going to the right. We are doing it based on this top view. Okay, so according to Lenz, you like just to oppose only. So since the change is a decrease, so I just increase magnetic field which is going to the right. So based on what I would like to increase, I have to produce. Okay, since I would like to increase magnetic field which is going to the right, so I will produce the magnetic field which is going to the right. So now you have already know the induced magnetic field that you would like to produce which is going to the right. So using your right hand grid rule with your thumb pointing to the right from the top view, yeah? So from the top view, which means now your finger is your coil, right? Your finger is your coil. So it is actually, if it is now in front, your finger is now facing you. Okay, so what you have to do now, since we are looking at the perspective of top view, so what you do is move your finger, move your whole hand beneath your head, your finger on top, from the top. So where pointing when the coil is on top, when the coil is just below you, isn't it going downward? My camera, I don't know what happened today, it doesn't allow me to open. We can't connect to you install properly, or are you using it in another application? I don't know what happened today. Yeah, okay. You on your hand. Okay, so now on your hand itself, hold the coil, and underneath your, how to say, put it as below so that you can see the top view of the coil. Okay, put them in, like, let's say, did you print out your worksheet, or you are all looking at your computer screen? Or you put them on top of your table, table, which means you are now looking on the top view of your coil. So hold your coil with your left hand first, and now use your right hand to determine the direction, yeah? Okay, so it's going to the right. So compare your finger now, your right hand, with the coil. With magnetic field going to the right at the center of the coil, on top of the coil, now what is the direction of the current? Can you imagine? Kema. Can you get that? How say clockwise or anti-clockwise? Okay, so I will see if, okay, only allowed me to turn on my back camera, yeah. Okay, so let's see. Can you all see anything? Cannot, huh? What happened? Yeah, I also don't know what happened to my laptop today. Yeah, okay. Can y'all see now my hand? Okay. So, okay, let's say this is your coil, yeah? So I'm now treating the camera as your top view. Okay, this is your top view. It's from your perspective, yeah? So this is the top view is here. Here is side view. This is also side view, can? You have to imagine in that way. Yeah? So if now this is your core, you are actually looking at here. This is your top view. So let's say here is right hand side. Okay, this is your right hand side and this is your left hand side. So if I would like to have my magnetic field which is going to the right hand side, so compare your finger now, right hand side here. So on the top view, where will be the direction of my current? Isn't it going this way, going down, going this way like this? Here from here to here. Can? So if you compare with your questions, how to show it? Okay, so now let's compare it with the question. So now look at your screen, yeah? Okay, this is our based on the question. Okay, based on this question, isn't it okay, this is our top view now here. Where is my camera? Okay, this is our top view, correct? And now we would like our magnetic field to be produced in this direction, to the right. So compare your right hand grip rule with the coil. So right hand grip rule here. Oh, my hand. Like this. Right. Right hand grip rule. So this is how your current will go based on your finger, right? Here, like this. So when it comes to the top view here, the direction, isn't it just going downward? Imagine that 3D, the current has to be moved from here, further away, up, come towards you, and just right on the top view here, your top view, isn't it just going downwards? So that's why when you want to write your direction, because it is on the top view, so instead of you say clearly where is the direction, but instead if follow the top view, it actually just going downwards. Is it clearer now to you? Okay, huh? So that's why when it comes to the questions of this, unless you purposely mention from which you are writing, the clockwise or anti-clockwise, otherwise it's good to just follow the only. Okay, if the question shows you from the top view, then you imagine you are writing. Okay. So now let's look at question 5. He was asleep. Okay, you have a loop. So what we have here is we have to determine what is the induced current. Outer loop, there is a current flowing and the current has changed from 2 ampere to 1 ampere in 0.2 seconds. So firstly, write down all the information. The area we have for before is 0.0616. The magnetic field felt by the loop in the center. So according to right hand grip rule, when current at the outer loop goes in this direction, it will produce magnetic field which is going into the page. Both of them will produce magnetic field which is going into the page. The difference is the one with higher current will produce larger magnetic field, the one with lower current will produce lower magnetic field. So this magnetic given by solenoid. Turn is equals to 1 for the outer loop. So length is not length, sorry, it's not solenoid, it's circular coil, 2R. So 2 times the radius, which is 1. 1.26 times 10 to the power of negative 6 Tesla. Theta is equals to 0. Area doesn't change. However, the magnetic field felt change because the current decreases. Current is decreased to 1. 6.28 times 10 to the power of negative 7 Tesla. Theta equals to 0. So now from Faraday's equation, determine our induced current. So the changing, so take out the A, left only delta B minus delta C. Now plug in the value. Final B is 6.28 times 10 to the power of negative 26 times 10 to the power of negative 6 divided by time. So 1.95 times negative 6 volts. Rule to determine the direction. Okay, just now Jungfui has already determined it is clockwise. So let's see how do we get the clockwise. Yeah? So if you look at the change, since the current decreases, so the magnetic field produces decreasing. So that's why the magnetic flux experience a change in the decrease. So it will be decrease in the magnetic field which is going into. We would like to oppose the change. So increase cross product. So produce cross product. In order to produce the cross product, now into the screen. So the direction will be clockwise, or when it passes through the emitter, it is just passing from the right to left. Okay. Now left. The last question. Has Azim, have you? Are you working? I mean, have you worked out yet? Or is he still in the? Is he still here? Yeah. Maybe he went to shopping. Okay. Okay, so let's question 2 together. The coil is dragged upwards in 0.2 seconds while the magnetic field is kept constant. So, what is your answer? Anyone would like to volunteer? Anyone?